like 7 hours. Nobody knew. We all thought
She thought you were sleeping?
We thought we all
Oh,
thought she was
jeez.
asleep. Well, I went home and I get a call like an hour later. Turns out she had passed away.
It's like National Lampoon's.
So I was working for the same company, so he asked if I could cover the shift because we were supposed to work that day. I was like, dude, I got you.
Yeah.
I thought I was this freaking like 6-year-old kid who's there. I was like, how do you explain it to the kid?
You don't? You just say, oh, damn.
His kid's pretty sharp. He blatantly said, she died. Well, he's had like one other, like a goldfish in the past.
All right, guys. So I had a few people ask you a few questions. Anybody have questions from any homework stuff? So far? 4, 9, 6, 1.
You want to do 33?
1 through
6, 1?
the end of
Oh, 6, 1. Oh, yeah. Well, I mean, all right.
As I said, guys,
We're not going to review that because we're about to get into 6-2 where we actually solve them and we want to be able to check it.
so it
if
wasn't
we
just
do problems
me,
like
it's
that.
worded from, it's like that, reading into the next chapter.
Yeah.
All right.
Yeah, they do that often in calc-based courses.
It
Where they
wasn't
say,
crazy. Yeah, it was
here's
like-
a weird-ass problem, and then it becomes a normal problem. And then
Yeah, well, that's what I was like. Initially, I was like, there are no examples like that in any of the homework. But it's a 1 over.
All right, guys. Anything from homework stuff? I will address John's question in more of a
General
review kind
sense.
of thing.
That would be
I thought for
fine.
sure we did a problem. I could be very mistaken, where we had to verify the solution that was in a power series representation. We didn't do that yet.
No.
Okay.
That's why I wanted to ask you about it. 'Cause
We'll do that.
I wasn't sure about that 1 over n, or because it's alternating.
That's why we did what we did last time with the handout.
It wasn't me being stupid.
Anybody not get the handout from last time? The series practice handout? So it's on the video. If you want to go see the video, we worked it out. I believe. Did we do this? We finish this?
Yeah.
yes.
Thank God. Okay. The whole thing about number 2, of course, and number 3, those two skills combined are what you need to be able to check that a power series representation is a solution to some D. So, for example, yeah, I like this kind of problem here because somebody tell me, do we have a method? Well, this problem isn't exactly what I'm thinking about. We do have a method to solve this kind of problem. What method would you use to solve this, unless you were told, as you are here, to do something else?
Integrating factor?
All right, so you could use an integrating factor. Or?
Ask the mathematician.
No.
Oh, separation.
I am asking mathematicians.
Separable.
Yeah, separable. I love it. So
Engineering.
integrating, separable. I love it because that's 0, so you can actually pull it over. It's all multiple, so you can break them up. I love it. Okay, here we're not even going to solve it. You could solve it on the side, see what the answer is. What I love about some of these problems, I kind of hate it when they give you a problem you can solve an earlier way, but and then they ask you to solve it using series. The nice thing about those specific problems is you can solve it, you know what the answer is supposed to be. When you get the answer in series form, you want to compare that to the table on page 239 where they give you well-known power series for different functions. I like it. So I really want you guys to understand like cosine x being the series that it is, it's almost as if we didn't do this, but it's almost like that series is defined to be cosine x. I mean, but then you have series that don't have a corresponding function with them, right? And then your brain starts to go, well, could there be? Could we define a function to be that? And then you could kind of follow that logic. We're not going to go all down that road. So here they say verify that this is a solution. Where you go? Where are you at? There you are. All right, so we need to verify that that's a solution. So we only need one derivative. That's nice, right? When you take this guy's derivative, what's going to happen? We'll put this on here in a minute. This stuff, what happens to this stuff? It's multiple. So this is a constant coefficient given any value of n. So it's going to stay exactly the way it is. what happens here?
N equals 1.
How do you take the derivative of x to the 2n? How do you take the derivative of x to the anything? Yeah, the power comes down in front of it, and it goes down by 1. Like, don't overthink it. Don't make it like 2n minus 2 because there's a 2 there. No,
And then your
whatever the
n would
power is,
go
it goes down by 1.
Up by 1, right?
See again?
And then
When you
your
integrate,
index would go up
it
by
goes
1.
up by 1, you divide by it instead of multiply by the old one, and then write the new one.
This one.
I like it because inversion is the opposite. Blah, blah, blah. Okay, so now I can throw this stuff in. Now here's, so this is what was it? On that, number 2 on the handout was all about taking the first and second derivatives. We only had to take one derivative here. Number 3 is all about putting together summations. So here, if I throw this in here, I get, oh yeah, where's this start at? It could, but it starts at 1, because when you make 0, what do you get? 0, so there's really no point. Now what's interesting is you could actually do something between these two, right? If you want to. Let's see if you want to. So if I throw it in there, I'll get plus 2x times the sum by the way, I mean, I know it doesn't, people always have, I understand having trouble working with summation because you don't work with it all the time. So you have a little bit of trouble remembering how things kind of work. But you shouldn't be like trepidatious about it. It's just a polynomial, right? It's or worse, you know, a few negative terms. It's just a infinite. It's just things added together. So that's why the derivative is so easy, because I can do the derivative of each term in the summation. That's why I can just do it directly to this thing. It's beautiful.
And you could do make n minus 1.
Yeah. How do I keep going here?
First,
What can I do with this?
Multiply. H bar.
Yeah, bring that in. I can bring the 2 in, or I can bring that 2 out, but that 2 being in both of them makes me feel good. Okay, maybe. We'll see. So I can bring that in. So I'm going to just leave the 2 out here. Why not? So that becomes negative 1 to the n over n factorial times x to the 2n plus 1. I like it. Blah, 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 blah. What can you do here if you wanted to? I don't know if you even want to, but yeah, we could. Yeah, so what would you be left with? Let me take a 2 out of there. So this would be n times, so then it becomes n minus 1 factorial, x to the 2n minus 1, and equals 1 to infinity. All right, so how can you put these together?
well, you get your x of n to be the same.
Yeah, you want the powers on your x to be the same. I like it.
And then you make your indexes the same.
Then you make these the same. I like it. So how do you make these the same? Who are you going to mess with? It doesn't. All right, if you mess with the first one, you got to think about it. How to make that become that? I have to let n go to be what? N. Well, n minus 1 would make this.
Plus 1.
Yeah, n plus 1 would make this 2n plus 2 minus 1 would be 2n plus 1. Let me stop there for a second. Yeah, so if I let n go to n plus 1, so this would become negative 1 to the n plus 1. What does this become? N factorial, kick ass. And then this becomes x to the 2n, 2n plus 2 minus 1, so 2n plus 1. So now the powers are the same. I made them like terms. I love you guys. So let me see. Which part are we having the most trouble with? Right here, this is letting n go to n plus 1. So if you work that out, you get 2n plus 1. I like it. Now, what happens here? Yeah, n equals 0. I like it. And let's let's see. Yeah, I guess I'm gonna have to write that again. Now, can you guys see where this is going? I mean, what do you want to happen here so that you actually get 0? What has to happen? These two series have to be equal but opposite signs. And they're basically equal. Let me just change this to that. Maybe I'll get that. Look. They have everything the same. The only thing that's different is the one thing that allows them to be different signs. Right? This is -1 to the n plus 1. So can't I just take one of the negative ones out?
Yes.
So now how many negative ones are there in here?
And
And now they cancel.
Wait, sorry, can you repeat that?
Yeah, all right. Let me do it in 2 steps here. I'm trying. I'm just so lazy or tired. One of the two. So if I rewrite this, can't I? Isn't this -1 to the n times -1?
yes.
So can't I take that -1 out? So then you're just left with -1 to the n. Now they are exactly the same, different signs. Yeah. So then we verify 0 equals 0? Check. Like with my algebra students, do get here and they say all real numbers. No, you're checking. You just check. That's the answer over there. There. So that's why I focused on that skill of the 2-step skill. Make the powers the same and then worry about shucking anything off. We made the powers the same and thankfully these became the same also. That's super nice. I didn't have to worry about taking any terms away or separating terms out. Okay. So here, I'm going to let you guys try one of these yourself. This course is going to be harder than what we just did. Haha. Let's see. Here. Verify that this. Is that the one we just did? No. Good. Solves this. Sorry, this one is nice. This one is gross. I love it. All right. Just so you notice, you're going to put a series here where y prime is, right? Right. And then you're going to, yeah. A series plus x squared times the series. Okay, I like it. This is more of a puzzle. It's kind of nice. Some of you guys are like, that doesn't help. All right. So
Layers of
at least, Pinhead didn't come out and do stuff to you once you solve it. So there you go. Let's see. We have such.
We're not solving a box.
Yeah, don't solve the box. Leave the box sitting on the ground if you see it. You'll notice, I mean, this DE should look very interesting to you. I mean, it's like if that wasn't there, what does that kind of feel like? A type of Cauchy-Euler. I mean, it's got a one more power on the x, but the x is can't one x could divide out anyway. Yes, well, x can't be 0 already, so you just divide by x. But that being there throws that off. This is a very interesting problem. Now you could still actually, how could you do this anyway? Again, since this is one term, subtract, everything's multiplication, you could break them up, right? Wouldn't separable work? dy over y equals negative 2x over 1 plus x squared dx. Yes, sir?
How did you get all of your x squared and your 2x out front of the summation?
So here's
go away?
1 times this. 1 times this is here.
Yep.
And then x squared times this, so now this goes up by 2.
Okay.
Right? So I just brought the x squared in.
Okay.
And of course, x is a constant compared to the summation symbol. As far as the summation symbol cares,
Yeah.
x is a constant. So I can bring that in, raise that up by 2, and then this guy bring that in, raise that up by 1.
So you have the same exponent to the edge.
I like that.
And then you just make your ends equal.
The nice thing with that is these are now like terms,
You
just
solve
offset.
for either
This
one.
is not like terms, so I better take care of this guy first. Yeah, the n plus 1 thing we did a minute ago, so now it starts at 0. Negative 1 to the n plus 1. Got it. 2 times n plus 1, x to the 2n plus 1. I might as well bring that 2 in there. There's a lot of flexibility with what you can do here in terms of little things like bring the 2 in around it. Equals here. So these two are kind of the odd man out at the moment, right? I need to adjust the ends. So if I take this first term out, what do I get? When I play 0 in, I get negative 2 x to the first. I might as well write that next to its power. Now it starts at 1. Yeah. So taking one term out doesn't change the notation, doesn't change the function of it. I just took the first value of n out here. The function doesn't change. To change the function, I have to shift it in the n axis, if you want to think of it that way. So now I've got this like terms. So now I got, where'd it go? Hopefully some of you guys see where this is going. This guy doesn't need anything really. Actually, between these two, this guy needs something. That's right. That's right. What do I have to do with this guy now? Take out one term. Okay, you guys, you gotta, to get to this level, you have to have developed an ability to focus on the part of the problem that you care about at the moment. So if you still have an issue where you're looking at all this at once, when I allow myself to look at all this at once, I go, oh, all right. But right now, all I give a shit about is the ends weren't the same. I want to take the first guy off now. He's 1. He's cool. I want to take the first guy this out. Who gives a shit about that stuff right now? So the first term in this guy would be what? No negative, right?
Positive.
Positive. 2x, which is looking good so far. That's a nice thing to happen because I want it all to be 0 at the end anyway. Let me pull it up here. All right, and then the only things left are these. They're supposed to. Oh, I've left off there. I left off this. If I pull that first term off, this is now starting at 1. So now it's like terms all the way with what's kind of like the piece? Do you notice how this has an n plus 1? This has an n. This doesn't have any n's, right? But notice also that this guy has an extra negative 1. Do you see all that? I mean, that's what you should be looking for. You want to look for like terms. You can see the differences between the two. These are the most like terms that are down there, right? Mm-hmm. The only problem is this is n of these plus 1 of these, which is, of course, so if I have n x's plus 1x, I can rewrite that as n plus 1x. Yeah. Which is nice because the first guy there has a freaking and an extra negative. So these two become this, and then that guy is negative that. And you can kind of see that happening. So this should have been this should have been like, oh shit, what the hell am I going to do with that shit? So you're looking, okay, between the other two, this one's got n and 1. That didn't look good. So then I got n plus 1 between the two of those. So this will be, this first guy is just sitting there. Let me take the negative 1 out. Is that cool? The extra negative 1? Take it out. And then that's negative 1 to the n. Let's see, 2, n plus 1, x to the 2n plus 1. And if I add these together, I'm going to get the exact same thing without an extra negative. And that is 0, check. Does everybody see that? So I got n of these plus 1 of these is n plus 1 of those. That's all that happened there. Maybe if you just to focus on this piece for a second, this piece right here, this plus this. If I write one big summation, get out of the way in a second. And here goes 1. Negative 1 to the n. We put an n in front. And negative 1 to the n, 2x to the 2n plus 1. Plus negative 1 to the n, 2x to the 2n plus 1. So that's going to be n plus 1 times this. That's the GCF I can take out. Okay, I think I've said that as many different ways as I can think of. These verification problems are nice because you know, in this case, you want to make it 0, so you're looking for things to cancel. You can quickly tell what's wrong or what to do, how to make things go. All right, how's that feel? Is that all right? So that's exactly how you do number 33. We basically just did 31 and 32, and your homework includes number 33. So, okay. And, you know, it, of course, has a second derivative you have to work with, but yay. Okay. Anything else from homework stuff? I want to remind you, at least make sure you've seen, I can't remember if I asked you this, has everybody seen the proof of this? You should see it in 280. All right, everybody seen it? I will save you from seeing it again then. I like it. All right. So we got the one from this here. Okay.
Except the very last.
Okay. All right. So what we're getting into today, let me go ahead and give you this handout. There it is. We're getting into the first level of DEs that we can solve using series. Some of them will have functions that they're equivalent to, and some of them won't. up there now. Okay. I'm going to write a couple of these down here. Got it. Let's do one that we don't normally see. Ooh, yeah, let's cross it.
Try to do that.
Sure, why not?
Do ln to a sign.
Well, this is a normally this is the one that you kind of start with. I don't even know if you guys remember. You know, I could do sine x. Now notice, before I write this down, the power series, the summation notation for that, what is it about, even this one, let me go ahead and write this one down. So even this one follows a basic rule. Right. In this case, it would be n minus 1. How do they want to do it? They start at 0. I can do that. Okay. So hopefully you can see this even with the sign. What is it about what is different between these three? What's fundamentally different? Now sine looks very different from these two. Right? What's the same between these two? Oh, that's what's different between those two, yes. What's same is x to the n. And then this guy, the cn's are 1 over n factorial. What's the cn's here? 1. Right? And then here, notice that for this guy, the reason that this is different is because there are some c's that are 0. So for example, c0 here would be 0. c2 is 0, so forth. So that's why I can write this a little bit differently. It's only the odd powers that survive. You guys with me? My point is, every single Maclaurin series, Maclaurin meaning centered at 0, has to have this look. And you can have adjustments made to it depending on if there's a better pattern that you can capture more efficiently, all that kind of stuff. But they all basically come down to this. So in order to find what function is the answer, what is it that I need to actually find a relationship to? What is it that actually defines a function in this notation? C sub n. So if I can find, if all the CNs were related to a certain number, or all the CNs were related to a certain constant that was left open, you could pick. That would mean I found, if they all became this, that would mean the answer was e to the x, so forth. So if I use this power series approach, in fact, that might be a good idea to do. That might be a nice one to do. The whole process focuses on the CNs. So let's try one out. Let's do this. Can you guys help me create help me to create a second order DE that has this as one of the solutions? So let's go ahead as a class. Let's pick what the second solution would look like. To be nice to ourselves, don't make the second solution something crazy. So it'll be e to what? Let's say e to the 2x. I love you guys. That's awesome. 1. Let's go 2. So
That'd be crazy.
where would that have come from? Where would those answers have come from?
M equals 1 and 2.
Yeah, so this would have come from m equals 1, and m equals 2. So this would have been m minus 1, m minus 2. Right? M squared minus 3m plus 2. So what would the DE have looked like? Y double prime.
Minus 3y prime.
Yeah, don't forget that poor little y dude. Okay, so let's do this. Let's solve this. I know we know the answer already. That's why it's a beautiful one to do it as an example. We're going to get series solutions because we're going to start with an assumption about the look of the answer. This, by the way, they have on page 239, they have a whole table of these. I just picked out a couple. So I'm going to assume the answer looks like, so centered at x equal to 0. Solution to, where'd it go? Y double prime minus 3y prime plus 2y equals 0. So I'm going to assume the solution looks like that. So the instructions would say find a power series centered at 0 that would be a solution to this DE. So what's the very first thing we would do?
Take y prime and y double prime.
Yep. So I'd take y prime.
Cn
X and minus 1.
times n x minus n minus 1.
In fact, I mean, if you start to realize, we're always going to assume this when they ask me to find a power series centered at 0. So all of these are going to be the same every single time. So it's a good idea to get to know these really well. So what's y double prime going to be?
Cn n squared minus n.
Whoop. Good. N equals 2. Yeah. And now you throw those in. Now here's where things are going to be different. This is not verifying a solution because we are throwing in there something that's not even defined yet. So this is basically almost exactly. This is basically constant coefficients. We just assumed nth degree polynomial to be the answer to this. Obviously it goes to infinity, but just to say it's something really quickly. Right, with all these different coefficients. So we're actually going to find all the coefficients. So it's not going to be an infinite matrix to solve, thank God. We're going to get recurrence relationships. We're going to get a relationship between C8 and C0, C9 and C1, however it kind of plays out. So the feel of this problem is going to be the way that most of the problems in this section are going to feel. So I'm going to throw this in. Let's see, Cn, I got it, n minus 1, Cn, x to the n minus 2, minus 3, let's go ahead and throw the 3 inside, equals 1 to infinity, 3n Cn, x to the n minus 1, plus the sum, 2 Cn, x to the n equals 0. So again, now you really start to see why I focus so much on the approach to combining power series, summations, right? What do I need to work on to get these combined?
Change to 0 and 0.
Yeah, but very often what we do is we try to make everything n. You actually do not have to. If everything was n minus 1 except one dude, then make that one dude become n minus 1. Why the hell not? It's all about making like terms. The recurrence relationship you set up won't give a shit that it starts at n minus 1 instead of n. Who cares? But here, I might as well make them all n. Gotta make them all something. Might as well make it n. So how do I make this guy become just n? Start at who? Yeah, I want to make n go to n plus 2. I like it. So n plus 2, n plus 1, c sub plus 2, x to the n, starting at 0. Why do I start at 0?
Because if you offset it by
Shifted
2.
it by 2, you can kind of double check. When I plugged a 2 in, I got a 0 here. When I plug a 0 in, I get a 0 there. I feel good about that. You can check the entire first term if you want to really be sure about it. Make sure you didn't miss anybody. And this guy, of course, I just have to shift in by 1. So this is looking kind of like a nice problem. This was nice because there's no x coefficients that are throwing things off further, right? So here I get 3, n plus 1, c sub n plus 1, x to the n. And then I got this poor little dude at the end. Whew. Okay, so this guy is scrunched up there. Okay. So, I mean, I know these are power series. We're not as used to working with them, but this is exactly the same thing we do. We assume the form of the answer. We get the derivatives, throw it in there, start to work with it. Let's see, now I can combine these. Now here's, can I combine these? Let's see, they're all zeros and they're all x to the n's.
Why not?
I like that, why not? So now here's what I'm going to do. I'm going to take an x to the n, I'm going to put it at the very end. I'm going to take it out, basically. So then I got n plus 2, n plus 1. Did you give yourself enough room? Let's just not do that, Jeff. There you go, buddy. Cn plus 2 minus 3n plus 1 cn plus 1 plus 2cn x to the n equals 0. Now this is supposed to be 0. Always, right? Whatever value of x I pick, any value of x I'm allowed to use, this has got to come out to be 0. So therefore, what must be true?
It's got to be 0.
X doesn't, yeah, I can't
Can't
force
be
x.
zero, so the
This whole thing
must be 0.
must be 0. Remember our answers were give the x and give the 2x. Now I've got
Next page.
all right. Here's the idea. I don't know how much you guys have worked with recurrence relationships with. You pretty much always want to solve for the one with the highest index, because then it's based on previous values. So if I solve for Cn plus 2, I'll have a formula that will get Cn plus 2 given any values for the previous things. And how many guys have done like this is not going to be this, but how many guys have done math induction stuff? Anybody? One of you? I'm going to have to show you some freaking math induction. I can't let you escape. Get any kind of math-related degree. Never done induction? I'll be right. It's not got anything to do with it. If I solve for Cn plus 2, can you guys see what's going to happen? I'm going to add this over. You just add this, subtract this, divided by the coefficient of this. If you wanted to, you could break those up and cancel the n plus 1s. Doesn't really matter. If I try to make n negative 2, what happens? I get C0, but what happens here? Yeah, if I try to make n -1, I try to get C1, but what happens here? Oh shit. So C0 and C1 are unrestricted. They are the true constants. Every single other constant is going to be based on them through that recurrence relation. So that's, again, before you've seen it happen, you're like, oh, what the hell you just said? Let's just do it. So if I want, so I know C0 and C1, I know them. They're whatever the hell I want them to be. So now let's start, what's C2? That would mean n is what? So I always, for myself, my own sanity, I always write out in front. N would be careful.
0.
0. So to get C2, I make n 0. So what do I get up here? 3 times 1 times C1 minus 2C0 all over 2 times 1.
Wait, oh, if we just plug one and 0 into all that.
Exactly. And again, how do we get that? C0 and C1 have to be undetermined. They're completely free. Sort of like Fibonacci sequence, you got to start with 2 to get it started. When I say Fibonacci sequence, do you all know that? 1, 1, 1 plus 1 is 2. You got to start with something. So if n is 1, I can then figure out what C3 is.
So did we just chose 0 because it's easy to work with, or
No. We chose 0 because that's the way to get C2, which is the first constant that I have that's defined on the other two. If I try to let n be -2, which is how I'd get C0. If I try to let n be -2, then I get an undefined occurrence, right? If I try to let n be -1, it's undefined. So the first value I could really use is n0 to get C2. C0 and C1 are completely free to be whatever I want them to be. Just like any YC is going to have. Okay. And how many answers should I get to this thing?
3, 2?
2, right? So it makes sense there's going to be a C0 series that I can kind of get together and a C1 series. And that's going to be the 2 answers. One's going to be controlled by C0, the other one's going to be controlled by C1. And very quickly, can somebody tell me the first few terms of this? C0 plus C1 x plus 2x squared, da da da. So all we're doing right now is figuring out what those are. 2 of them are unrestricted. That should make sense. Right? Because for a ox-aw thing, I'm going to get C1 something plus C2 something. In this case, it's going to be C0 something and C1 something. All right, if we keep going, C3 would be n equals 1. Trust me, my God. It's going to be, if you don't do this for yourself, you're going to be pulling in 3 ends and all the ends. You're going to get all kinds of weird shit. N is 1 to get C3. Is that cool? So then you get 6.
Why is n 1 to get C3?
So Cn plus 2 is this stuff. So how do we get C3?
Oh, so 1 plus 2 is 3.
I'd make n1. Beautiful. But I mean, that's so easy for your brain just to go, I'm working with 3. Yay. No, brain. Stop it. Shh. Tell yourself what the hell you're doing. So I get 6C sub 2 minus 2 C1 divided by, 6. I like it. Which is C2 minus C1 over 3. Let's go ahead and separate this. This is 3C1 over 2 minus C0. Got it. C4 would be n equals 2. Yeah, so you'll get 9C3 minus 2C2 over 4 times 3, 12. The nice thing is I can pull this apart and then I can step back and see which is the better way to look at this. Yeah, can you see a pattern here?
Is it factorial or something?
Yeah, so maybe I shouldn't reduce these, right? I mean, this is what you're looking for. You're trying to find a pattern. You can reduce it, but if you reduce it, you might lose the pattern, right? So it looks like you want to be 3c1 over 2 factorial minus 2c0 over 2 factorial. This is going to be 6c2 over 3 factorial minus 2c1 over 3 factorial. Now I can see if reducing those would help me. This would be 9c3 over, now is this a factorial?
No.
No, so then maybe, so this is 1 times 2, this is 2 times 3, this is 3 times 4. I like it. This is beautiful. So this is the kind of, the steps you need to take to identify the pattern. It's not a problem to take a guess. You start going and go, wait, that doesn't follow the pattern I thought it was. So you go back and you say, okay, that can't be the pattern. This was kind of, looked like it was factorial because that 1 threw us off. So this should be 2 times 3, 3 times 4, 4 times 5, right? So let's see. Maybe we'll leave it alone for now. I could say this is oops. Now here we got 3, 6, 9. Here we got apparently 2, 2, 2, right? But what's important is, now notice this. I need to have everything based on C1 and C0, right? I mean, this is the idea. I want to have like y equals C1, y1 plus C2, y2. In this case, it'll be C0 and C1 instead of C1 and C2. So, so C2 is this, isn't it? So I can replace, go back a step here. I can replace C2 with, isn't C2 equal to this?
Yeah.
So I can replace C2 with all this business. Whew. Oh boy. Maybe this wasn't as nice of a problem to start with as I thought. But still, I mean, this one is a little worse than some of the basic ones you'll see because it's got a mixture of 2 here. Most of them won't have that. It'll be C0, C1, C2, C3. It'll be a little easier to kind of work with. But this isn't too bad when you realize you want everything in terms of C0 and C1. Now what happens here though, this is interesting. So I get 3, I'll get 9C1 minus 6C0 minus 2C1 over 6. So I'll get 7C1 minus 6C0 over 6. Yummy, yummy. And then this one, you know what C2 is, you know what C3 is. That one's gross. All right, so let me reel it back. I was a little overly hopeful. I wanted to come up with a nice series at the end that we can identify as being an e to the power or something. I made a little bit more disgusting problem than I wanted to. So let's try it. Let's do the one I really, really wanted to start with, which was, let's do a problem, then I'll come back. We'll talk about terminology. All right.
Freak out.
Don't freak out yet. I made that problem up out of nowhere, so I really didn't know ahead of time what that was going to lead us to.
Well, in order for it to be e to the x, right, it has to be equal to the series 1 plus x over 1 factorial, so it must be similar to that one.
Yeah, once you get once you get the C1s and C0s, everything based on those, you would be able to take all the C0 stuff and all the C1 stuff and identify them each as an e to the x series and an e to the 2x series. Yes. Cool. I don't know if I want to sit here and do all that before you guys even see all the steps as they are supposed to be. This is a good maybe 4th problem to do. I got overly excited about a problem we knew the answer to already. Let's do this. Let's do this one. I like this one. Actually, this is one we know the answer to, but it's not going to be quite as horrific. Can anybody just see the answer to this?
Cosine 2x sine 2x.
Yeah, yeah. Because the second derivative would have a 4 if the inside was 2, right? What is it about cosine and sine that makes it this beautiful for that? There's a plus in the middle. And after 2 derivatives, they will both become opposites of each other. And since that's a 4 out front, I need an inside that after 2 derivatives will become a 4 out front. So 1 derivative 2